Okay, hello everyone. I am Suprio, Bhar, the instructor for the ongoing NPTEL course on Measure Theoretic Probability 2. I hope you are enjoying the course, and this live session is exactly happening at the almost at the midpoint of this ongoing course. So it is now a good point to have a live introduction session. So please post your queries if you have any. So as you are already aware, some Google form was already circulated where some of you have already shared your queries. So I will take those up first and do some discussion. But you are also welcome to post your queries in the chat box. Okay. So let me take up some of the questions that were already posted in the Google form. I'll first take up the comment from Mr. Osman Dogan. So I hope I have pronounced it correctly. If not, I apologize. All right. So thank you first of all for your message of appreciation. So let me just read the question part of your comment. It says that my question is about the modes of convergence for the vector of random variables and matrices of random variables. That is, let xn be any n by 1 random vector or n by n random matrix, then how can we consider the modes of convergence for xn? Probably we will use a vector norm or a matrix norm to define the modes of convergence. Since there are different vector and matrix norms, does the convergence depend on the vector norm or matrix norm that we adopted? For example, can a random matrix converges in the row sum norm but not in the column sum norm? Thank you. Best regards. All right. So let me take this up. So the framework of the question is pretty general, I would say. So we are trying to ask how we can generalize the modes of convergences that we have already seen for the for the random variable setting to the setting involving random variable. So that's essentially what the question asks. So for example, if we take up the question involving almost sure convergence, then what you are suggesting is exactly correct, that you would like to bring in the appropriate norms while considering the corresponding pointwise convergence. And then again, if you want to extend these ideas to certain LP type convergences or even convergences in probability, you just have to replace the appropriate modulus that we were using for the random variable setting to your favorite norm. Now, just to clarify, please note that if you are working in a finite dimensional vector space setting, then what would happen is that if you have two different norms, then what can be shown is that there is some sort of equivalence between the norms. So if you are trying to define a kind of a norm, and through that norm you are trying to get these three modes of convergences that we have seen so far, then essentially the analysis would go the same way. However, just to be clear, we also have these matrix norms that you have pointed out. Now, these matrix norms need not be exactly equivalent with the usual norms that we use on these finite dimensional vector space setting. So we'll have to be slightly careful in handling those. So the idea essentially is that yes, you can essentially extend these same ideas when you are going to the higher dimensional random vector setting and talking about the corresponding convergences, in particular these three types of convergences that we have seen. However, just so that you are also aware of this, we are also going to see a fourth mode of convergence as we go along. And there, in fact, we are going to see some explicit examples and discussions involving the higher dimensional analog of that fourth mode of convergence. So as a examples of those, as some examples of those, we are also going to consider some other examples involving this random vectors convergence using the earlier three modes that we have already seen so far. So that discussion, I hope, will come up somewhat later in the course and will be hopefully a good enough addition to whatever we are discussing now. So please wait for that, and definitely that will be a interesting addition to whatever you are asking. But just in the setting of what you have already asked, the first three modes of convergence, we can definitely try to extend these notions using the appropriate norms that we can impose. But here we are essentially saying that my random vector or our matrix are actually essentially taking values in some appropriate linear space. If your space is not linear or where you don't even have a norm, then these discussions will not be possible to be extended. So just be careful about those. But there are other ways we can try to extend if you have any kind of a distance function. So you use the distance function and try to capture these different modes of convergence. So I hope this answers your question. Though your answer was pretty general and it's difficult to completely cover what are all possibilities, but I am just trying to give you some ideas on how these can be extended. These ideas can be extended. All right, so thank you for the question. Okay, so I'll move on to questions from Mr. Dhruvo Prakash Vishwash. So he has two questions, so I will take them up one by one. So the first question reads as like this: if two laws are provided, one can construct two independent random variables and their laws will correspond to the mentioned laws. My question is, if two laws are provided, when can one construct dependent random variables? In such situation, is correlation coefficient mandatory to know? Further, suppose laws and correlation coefficient of two random variables are known, still how one can construct two dependent random variables with the suitable laws and the correlation coefficient. All right. So this is something we have commented on during our discussion in week 2. So just to recall, we have pointed out that using the product measure approach, we can construct random variables with specified laws which actually turn out to be independent. So this is for finitely many random vectors. Finitely many random variables. However, recall that we have only commented for the same when we are talking about sequences, that is a countable collection of random variable setting. Now this actually brings in certain technicalities involving the appropriate sigma field that you will be using in the infinite dimensional setting, that is for infinite product of the real line. Now a similar discussion if we want to do for the dependent random variable setting, let me give you some background on that. So it is again a pretty general question and it will be not possible for me to go over in explicit detail, but let me give you some ideas about it. So in the independent setting, what we are actually getting is something like this, that if two random variables x and y are suppose given, then if I know that they are independent, then I can immediately construct the joint random vector and talk about its law. Its law is exactly gets factored out into the marginal laws. So this is what the application of the independence plays in. But now, if two random variables are given and I know that they are dependent, then in general, it's difficult to say what is the joint distribution. So So in the case of independence, we can explicitly say that the joint distribution exactly appearing as a product of the marginal laws. But in the dependent setting, if we just know the marginal laws, it is not possible to say for certain what is the joint law. So that is the difficulty that you face if we are dealing with dependent random variables. Even if we are aware of the correlation coefficient, that is still may not be enough to specify the joint distribution. So let me take up one explicit example. Suppose I know that I have two Gaussian random variables, and even if I know their correlation coefficient, so I am assuming that they are defined on the same probability space, and we are aware of what is the value of the correlation coefficient. Even under that setting, I cannot immediately say that the joint distribution is normal. So this is quite a striking result, that if we are aware that the joint distribution is normal, then definitely the marginal laws are normal. So that is for certain. But even if we know that separately the random variables are normal, and even if we know the corresponding correlation coefficient, that is still not enough to specify that the joint distribution is normal. So there are multiple choices in which these joint laws can be found. So these are in some sense goes into something called coupling. So we are not going to discuss these notions in this course. Just for your information, the general framework that we typically apply comes due to some other result from Kolmogorov, that is called Kolmogorov's existence or Kolmogorov's consistency theorem. It essentially says that if you are aware of all these finite dimensional distributions, and if these finite dimensional distributions have certain consistency properties, then it is possible to construct the joint random variable, or sorry, the joint random vector with the specified distribution. So this is essentially existence or a consistency theorem that we are talking about. This kind of links the properties of the finite dimensional distributions with the actual joint law. So again, this question is again pretty general in the framework, and it will be difficult to cover it in sufficient detail. What I would suggest is that please look at Kolmogorov's existence or continuity theorem. One good reference is the book by Patrick Billingsley titled Probability and Measure. All right, so thank you for this question. So let me take up the other question that you have. So let me read it. As an application of Kolmogorov's zero-one law, any real valued measurable function with respect to tail sigma algebra is almost surely constant. Now suppose xn be a sequence of random variables converging to x in almost sure mode, then x is tail sigma algebra measurable function. Can I apply Kolmogorov's zero-one law here to claim that x is constant almost surely, or do I have some misunderstanding? So let me clarify a slightly erroneous statement that you have. So the point that if you are having a tail sigma algebra, then you first have to take independent random variables before applying Kolmogorov's zero-one law. So that is the first comment. So Kolmogorov's zero-one law works only when you are aware that the sequence of random variables that you are taking are independent. So I will now consider your question assuming that the sequence of random variables that you have taken are independent. So let's now consider the corresponding tail sigma algebra, and it says that all the sets in the tail sigma algebra has measure or probability 0 or 1. And as you have pointed out, as a consequence of this, we can try to say that the corresponding measurable random variables, measurable with respect to this tail sigma field, can be shown to be almost surely constant or degenerate. But now we go back to your explicit question that you are considering a sequence of random variables. Now I am assuming in addition them to be independent, and you are assuming that they converge to the limit random variable in the almost sure mode. Now here I would like to point out that together with independence, if we are asking for the almost sure convergence, this is quite a strong condition. So let me try to analyze this a bit more. So when you are saying that the sequence of random variables converge in the almost sure mode of convergence, what we are saying is that there exists a null set outside which we will have the pointwise convergence. But now, what does the pointwise convergence require? It is that I fix the sample point small omega. Then there, what we are asking is that given any epsilon positive, what we are getting is that there is a sufficiently large enough stage capital N, after which the terms in the sequence will be close together. But that essentially imposes some lot of restriction on the sequence of independent random variables that we are working with. Remember, if we are asking for the Cauchy property here, so that's something that is a necessary condition now. What we are saying is that after a certain stage, nth random variable and the mth random variable, their values will be close together. But this is quite a strong condition to impose together with the independence of the random variables. You see, you are asking now that any further random variables will be in a kind of a neighborhood of the values of the nth random variable. So that is quite a strong condition to impose, keeping in mind that we have already assumed the random variables to be independent. So in this setting, I would like to point out that we are actually going to have some further discussion on this point. And in fact, we will see a fourth mode of convergence, which I have actually pointed out in the discussion of another question that we are having right now. So the thing is that we are going to see a fourth mode of convergence, and there in fact we are going to explicitly talk about some nice examples involving independence, where we are going to talk about the convergences not even happening in probability, but in a fourth mode of convergence. But then what we are having is that there will be a sequence of random variables which will converge in a certain sense, but not even in the sense of convergence of probability, convergence in the probability sense. Now, the problem is that there we will see that independence actually hampers the type of convergence. That's something that you should keep in mind that we are going to discuss in the 6th and 7th week. Another thing that we are going to see is some explicit applications of this almost sure mode of convergence and the convergence in probability, some explicit examples immediately in the 5th week. Sorry. I think you may have already started looking at some of the lecture videos which have been shared already. But there we are going to see something called the law of large numbers. There we are going to talk about this series of random variables once more and look at some special type of series there. And we are going to discuss the convergence of these to degenerate random variables. So that's the type of thing that we are going to see. So I think that your question that we are discussing right now would be better served if we first see these examples and then come back to it, because we will then have much more explicit results at hand, and with that ideas we will be able to better analyze your result, better analyze your question. So we will come back to this definitely. So please note that we are going to have another live session towards the end of this course, and I will be sure to take up this specific question once more. And if you have any further questions, please post it in the chat box. And you are also welcome to post your queries as you are doing through the Google Group forums from time to time. So we'll try to keep in touch through the Google Group forums also. So now I think all the questions that were submitted through the Google form that has been discussed. So if you have any further queries, please feel free to post it in the chat box. Okay, so those who have joined this live session, I would request them to kindly post their queries, if any, in the chat box. Please post your queries in the chat box if you have any questions. So if there are no further queries, we can wait another minute or so. We can end the session then. Okay, so there seems to be another question posted. So let me read the question. In the tutorial week 4, I did not understand how can I prove failure in convergence of Sn over n in probability. All right, so the idea is this. So in fact, this is something we are going to also see while we discuss the content in week 5, while we discuss the law of large numbers. So this will also be relevant there. So let me just take up your question now. So the it was essentially left as a exercise for you that the with certain bounds on the probabilities that we are given on the original random variable, we are supposed to show that Sn over n does not converge in probability to 0. So now the idea essentially is that we have some explicit equivalent statements or convergence in probability, in particular involving certain kind of bounded random variables and their moments. So my hint is, please try them, try to get estimates involving those and see if those things are converging to 0. So that would be equivalent to the convergence in probability. So please try this. We will definitely continue this discussion in the Google Group forum. So please try this first and post your attempt. So that will be nice because we can then work with these hands-on computations and then continue the discussion like that. So if I just supply the answer, it may not be that useful for you. So what I would suggest is that please supply some attempt that you have made. So the hint essentially is that you try to work with the boundary random variables, which are like taken together with minimum one formulation that we have used, or even the ratio formulations, and these should go to 0 if the convergence in probability was supposed to happen. So please try this approach. Can you show that these corresponding expectations do not go to 0? So I hope this answers these questions. I'm essentially suggesting that please try out this approach, and we will continue the discussion in the Google Group forum. Is there any other doubt? If any, please post it in the chat box. Okay, so there is another query. So you are asking about Brownian motions. All right, so since this is beyond the scope of this present discussion, let me just quickly give you a few references. There are, depending on the type of properties you want to learn about Brownian motion, there are several references. One is the book by Peter Mortars and Yuval Perez. It's titled Brownian Motion, I think. And then there is another book titled Brownian Motion and Stochastic Calculus. That's by Shreve and I forgot the other author. Just let me try to recall. Karazas and Shreve. So these two authors have wrote a book titled Brownian Motion and Stochastic Calculus. So please, you can also try that, but that goes into the stochastic calculus route. There are other advanced stochastic processes books that you can also try as references for Brownian motion. But since this is beyond the scope of this course, I will not go into the further discussion. I hope that answers your question. If there are any other queries, please feel free to post the question. Okay, so since there are no further queries, we can end the session. Thank you all for joining the session. So see you next time on the next live session. Goodbye.